In this video, we will talk about compensation in acid-base disorders. And we know that metabolic acid-base disorders like metabolic acidosis and metabolic alkalosis would be compensated by the respiratory system by lowering the PaCO2 level or by increasing the PaCO2 level. Similarly, the respiratory acid-base disorders like the respiratory acidosis and the respiratory alkalosis would be compensated by the metabolic system by lowering or increasing the bicarb level. The next thing we need to know is how much compensation. These compensations could be too much or too little, indicating a secondary acid-base disorders, meaning a mixed acid-base disorders. Now let us look at how metabolic acidosis would be compensated by the respiratory system. In metabolic acidosis, a low bicarbonate level would cause the pH to be low, and the respiratory system would try to raise the pH by lowering the PaCO2 level. It does this by increasing the tidal volume and the rate of respiration. This is clinically known as Kussmaul's breathing, where there is a deep breathing as well as a fast breathing, driving the carbon dioxide out and subsequently lowering the PaCO2 levels. Now, how much will the PaCO2 be lowered? You can find out this by multiplying the change in bicarbonate by 1.2. For example, if the bicarbonate level of a given ABG is 14 milliequivalents per liter, meaning metabolic acidosis, the change in bicarbonate level would be 10, because the normal would have been 24 and the actual is 14, so 24 minus 14 give us 10. In other words, the bicarbonate level is deficient by 10. Now, how much would be the change in PaCO2 level? We can derive this number by multiplying the change in bicarbonate with 1.2. So 1.2 multiplied with 10 will give us 12. So there will be a change of 12 millimeter of mercury in the PaCO2 levels for compensation. Now the new expected PaCO2 in case of this ABG would be 40 minus 12, that is 28 millimeter of mercury, 40 being the normal PaCO2 level and 12 being the change by means of compensation. So in metabolic acidosis, if the bicarb level is 14 milliequivalents per liter, we would expect a change of 12 millimeter of mercury in PaCO2 levels, and the new PaCO2 levels would be around 28 millimeter of mercury. If this is not the case, say the new PaCO2 level is not 28 but something like 20 or something like 35, then the compensation would be too much or too little. In such case, there is usually a secondary acid-base disorder giving a mixed acid-base disorder, maybe metabolic acidosis with respiratory alkalosis or metabolic acidosis with respiratory acidosis. Now let us look at this example. The pH is 7.32, which is low, indicating acidosis. The PaCO2 is 23, which is also low, but alkalosis on the respiratory component. And bicarbonate is 16, which is low, indicating acidosis. So the primary acid-base disorder here is metabolic acidosis. Now we need to look at compensation on the respiratory component, that is the PaCO2 levels. In case of metabolic acidosis, where the pH is low, the respiratory system will try to bring back the pH to normal by decreasing the PaCO2 levels. So here in the ABG, the PaCO2 level is surely decreased, but we do not know whether the decrease in PaCO2 level is too much or too little for a given bicarbonate level, that is 16 milliequivalents per liter. So we need to find out with the formula, that is 1.2 into the change in bicarbonate level. So the change in bicarbonate level here is 8, because the actual bicarb level is 16, the normal would have been 24, so 24 minus 16 gives us 8. So we multiply 8 with 1.2, giving us 10. The change in PaCO2 level would have been by 10 millimeter of mercury. So the new PaCO2 level would be 40 minus 10, that is 30 millimeter of mercury. 40 is the normal PaCO2 level and 10 is the change, that is the compensation to metabolic acidosis, where the bicarb level is 16. So in case of metabolic acidosis where the bicarb level is 16 milliequivalents per liter, the PaCO2 level would have been 30. But here in our example, the PaCO2 level is 23, meaning the compensation is too much. Again, meaning there is not only compensation but also secondary acid-base disorder in the form of respiratory alkalosis. So the acid-base disorders of this ABG is a metabolic acidosis with secondary respiratory alkalosis. The point is, we need to know the expected compensation. Now coming to the metabolic alkalosis, the opposite will occur and there will be increased PaCO2 level by decreasing the tidal volume and respiratory rate, meaning the person would retain carbon dioxide. This response, however, is not as vigorous as the response to metabolic acidosis. So the change in PaCO2 in case of metabolic alkalosis is 0.7 multiplied by the change in bicarbonate. For example, if the bicarbonate level is 40 milliequivalents per liter, the change in bicarbonate would have been 16. And 40 minus 24, 24 is the normal value, would give us 16. In other words, the bicarb level is increased by 16 milliequivalents per liter. Now, how much is the expected change in PaCO2? You multiply 16 with 0.7 and you get 11 millimeter of mercury. So we expect a change in PaCO2 level by 11 millimeters mercury. Now the new PaCO2 level would be 40 plus 11, giving us 51 millimeter of mercury. Now coming to the respiratory acid-base disorders, the compensation by the metabolic component, primarily by the kidneys, is different for acute and chronic respiratory acid-base disorders. In case of the acute respiratory acidosis, the change in bicarbonate level is 0.1 multiplied by change in PaCO2, and in case of acute respiratory alkalosis, the change in bicarbonate level is equal to 0.2 multiplied by the change in PaCO2. And in case of chronic respiratory acidosis and alkalosis, the change in bicarbonate is the same, that is 0.4 multiplied by the change in PaCO2. So you can see here that in case of acute respiratory acid-base disorder, the compensation by the kidneys is not so strong, and in case of chronic respiratory acidosis and alkalosis, the response by the kidneys is more efficient. So what we learn basically is that in primary metabolic acid-base disorders, if the change in PaCO2 is more or less than expected, there is secondary respiratory disorders. Similarly, in primary respiratory disorders, normal or near normal bicarb means acute respiratory disorders, meaning in case of acute respiratory acid-base disorders, the response by the kidneys by means of changing the bicarbonate level is quite minimal. And again, in primary respiratory disorders, if there is significant change in bicarb levels, it indicates chronic respiratory disorders. Now, lastly, if the change is more or less than expected, meaning in case of respiratory disorders, if the change in bicarb level is more or less than what is expected, there is a secondary metabolic acid-base disorder. Now, let us look at this example. The pH is 7.54 and the PaCO2 is 23 and bicarb level is 16. Since the pH is high, it indicates alkalosis, and the PaCO2 is low, again indicating alkalosis on the respiratory component. So the primary acid-base disorder is respiratory alkalosis. Now, the kidneys would try to compensate this by decreasing the bicarbonate level. The bicarbonate level in this example is decreased, and it is decreased significantly, meaning the respiratory alkalosis is a chronic one, because in the acute respiratory acid-base disorder, the compensation is quite minimal. So the primary acid-base disorder is a chronic respiratory alkalosis. And the next step is to calculate the compensation, whether the compensation is adequate or too much or too little. So the formula is to multiply 0.4 with change in PaCO2, which is 17 millimeter of mercury. That gives us 7. So the bicarbonate level would be expected to be decreased by 7. Now the normal bicarb level 24 minus the change 7 would be 17. Here in our example, we get the bicarbonate level of 16 milliequivalents per liter. So everything is in order, and the ABG is chronic respiratory alkalosis with complete renal response. Thank you.